Another 1 minute, we'll wait, then we'll start. Already it is late. The class is going on or what? Hey, today, less strength. Are you able to hear me?
Yes, sir, you're audible.
Yes. The last class is over or not? It's still continuing?
Sir, still continuing.
Oh, still continuing. Okay. We'll wait for then 1 minute, we'll start. That's it. Okay. Okay, we'll start. I think 52%. We'll start. So last class we have gone through the process steps just for a review purpose. So initially a process has started. It joins. I'm not connected over it. So the process has started at the when it was at the secondary memory. When it started, it comes to the new state. During the new state, the process may not have a memory. Memory means here the primary memory. Once it will get the memory, it will come to the ready state. So if it is not getting any memory, there is a chances that it will go to the ready suspended state. Once a process has all kinds of resources except the CPU, then he is present in the ready state, and from the ready state, one of the process will be selected and going to the running state. And while a program is running, there are three basic possibilities. Either it will be dead, or it will be he himself has to be come out from this running state, or somebody force him to take him out from the running state. So if you can look into it here, so this is directly terminated case while it is running. He himself comes out because he needs some IO. And in these scenarios, we discussed that either one interrupt comes, that's why he has to be forcibly come out, or it's time, the quantum time gets over, then also it is comes out. So when it comes out, there are two ways are there. One is it will enter into the ready queue if the memory is available. It may not enter into the ready queue, rather it will be come to this ready suspended state when he has to come out, but no memory gets available. And this is basically called as the ready suspended. So another state we studied that once a IO requirement or any event is required, it comes to the block waiting state. Still the process is present in the RAM, but sometimes what happens that it is waiting for some event, but that event is not quickly executed, and you have a memory deficiency comes into picture. In that scenario, the process has to be bringing out from that memory, rather it will enter into the secondary memory, that is called as the block suspended state. And once the memory gets available, again it will enter, execute, and do its job. Once the IO events gets occurred, it will again come back to the ready state for further execution, because it has not completed, partially it has done. In the same manner, when it comes to the block suspended state, and that time the event has occurred, but he wants to go to the ready state, but the ready state doesn't have any memory. In that scenario, it will go to the ready suspended state. So these are the basic scenario we have studied. And if you can look into it here, one observation. So this particular states are basically present in the secondary memory. Okay, this is in the secondary memory. And these two states, you can feel like it is in the primary memory. Okay, primary memory. So when a process comes to the secondary memory, what is the reason? The reason is that there is no primary memory currently available, because of there is either the many processes, a high-end processes or high priority processes already present in the primary memory. That's why they are not getting. So in that scenario, it has to be swap out. So this suspended and resume from this primary memory to the secondary memory is basically called as the swap out and swap in. Swap in and swap out. Yes, and where it comes, basically you heard about a scenario called as the swap space. If you have remembered, or if you have ever run the install the Linux system, during the partitioning, you are making a partitioning of the swap area. Yes, usually we prefer the swap area is twice of your RAM size. If RAM size is 4 GB, preferably you are making the swap area to be 8 GB. So in this swap area, these things has to be take out from this RAM and put it in that swap area. And that swap out means moving out from this area, and again swap in means it is entering into this area. So that is basically called as a swap in and swap out. And all this movement from one state to another state, like many processes are entering into the ready state. That is one interesting part. Another interesting part is from the ready state, it is going to the running. And from the running, nobody will force you. If you can look into it, see, can you running, while it is running, you are coming out, or you are dead, or because of one interrupt, you are coming out. But in this case, few people are present, and among this, somebody has to be selective. Here also, when you are entering into the ready queue, there may be a chances that you may not enter because this ready queue memory may not be available. So that's the reason some program will be plays an important role, and which process will be moved from one state to the another state. That decision has to be taken by somebody, and that particular process is basically called as a scheduler. Yes, the scheduler is basically, you can say it is a program that takes the responsibility of moving a process from one queue to another. So what is this queues here? The queues is basically, if you can look into it, there are two kinds of queues mostly we have used here. So here one kind of queue is used, that is called the IO queue. And another here you have used here, this one is called as the ready queue. Yes, because there is a chances of multiple processes are present currently in the ready queue. There is also a chances of multiple processes are waiting for their IO event. And there is also another queue called as the job queue. Yes, as per the theory is concerned, or we are also following while designing this OS. The job queue means all the processes are belongs to this job queue when they are created, and after that it will be moved to the ready queue. Somebody will be moved to the IO queue. Depending upon that, it will do it. Then what the scheduler says, how a process will be moved, which process is going to be moved from one queue to the another or one state to the another, that decision has to be taken by a scheduler. Okay, because there are n number of processes present in the ready queue who will go to this running state. That decision has to be taken. But here there is no such decision. Basically, you have to come out, you have to come out. Then after come out, somebody will take a decision that who will enter. But for making come out, there is no such a decision. You have to forcibly you have to come out, or you yourself is saying that I am finished, I will come out, or I need an IO, I have to come out. But in this case, when this new state wants to send a process to the ready queue, somebody will take the here decision that whether I'll allow him to send it to the ready queue or not. That again takes a matter, because you have to look into it whether the space is available or what kind of processes are currently present here. So based on different criteria, it will be selected. That's why the scheduler itself taking a decision that among some certain number of processes, which processes will be go to this different queues. So on basis of this, the scheduler are basically of three types. Tell me.
In that block waiting to this block suspended when we go.
Block waiting to block
Suspended.
to ready queue suspended.
Block waiting to block suspended.
Oh, block waiting to block suspended. Okay, that last class I told in a very nice example that suppose you have made a scanf. The scanf is now process is now come out from the IO because you need a scanf. Yes or no? Once you stay here, then unless until a user gives the input, the next statement will not get executed. Yes or no? Suppose during that time the user moves somewhere else. Your cursor is still blinking. Do you think that that process has to occupy the memory or better to bring him out?
Yes, sir. Got it.
Got it, no? So that is the time when the process has to be move out from the block waiting state to this. Means since you have a limited memory, unnecessary those who are not currently using this memory for the right purpose, better to make him out. Okay, so that decision also taken by a scheduler. So what are the different kinds of scheduler? Basically there are three kinds. One is called a short-term scheduler. एक क्वेश्चन आता है, थोड़ा देख लीजिए theoretically, and one is called as the long-term scheduler, and another one is called as the medium-term scheduler. Medium-term scheduler. So this short-term scheduler is basically called as the CPU scheduler, and this long-term scheduler is called as a job scheduler. And this medium-term scheduler will help in to make a swap out and swap in. Yes, means if you can look into it, what is this CPU scheduler? The CPU scheduler's basic job is to, why it is called as a CPU scheduler? This scheduler takes a decision. This scheduler takes a decision about which process will move from ready queue to running state. Yes, means you can say as per this figure is concerned, so here actually the short-term scheduler work. Because among all the processes currently present in the ready queue, which one will be come to the CPU for execution, that decision will be taken by the short-term scheduler. Okay, so that's why it is called as a CPU scheduler. Means he is feeding the CPU, or you can say that he is giving the food to the CPU that you take this particular process and execute it. So that decision he is taking. That's why it is called as the CPU scheduler. And please remember, this short-term scheduler will be frequently executed. Why it is executed? Last class also at the end I have just given the view. When a process is executed here, how can you say that a scheduler will be enter and execute? Because without a scheduler entered into the CPU, he cannot also take a decision, because the scheduler itself is a program. Program means some algorithm must be written inside the scheduler. Unless until that algorithm will be run, one of the processes from the ready queue cannot be selected. Now the question comes here, if X process is currently executed, how a scheduler immediately enter into this? Is it possible for entering? Not at all. Then when this scheduler will be entered so that it can be executed? Can anybody answer? Last class little bit I discussed.
Interrupt table.
Oh, yes. One maybe one. Suppose when a particular process is executed, if any interrupt comes, so interrupt service routine program will be executed immediately, because interrupt service routine program has a high priority as compared to this one. So interrupt service program, when it will be executed, you can say inside the ISR, the scheduler has to be called. So what is first part I told? When the scheduler is going to be called. When the scheduler is going to be called. So first one you can say while executing the ISR. That is interrupt service routine program. Means if my interrupt service routine program is this, somewhere here I have to call a scheduler. Yes or no? If it is my ISR, think that it is my ISR, then inside this ISR, at the end, I have to call the scheduler. Because the moment my interrupt gets over, I have to bring a process from the ready queue to the running state. So the scheduler has to be called. That is one case. The second case is that, anybody? What is the second case? When a scheduler will be called? One case he has told.
Timer. As a timer.
That timer is an interrupt. That is one case you have told also. That is including this ISR. Anybody else? कब एक scheduler को कॉल होगा? इस डायग्राम देख के बोलिए. यहाँ पर एक प्रोग्राम रन कर रहा है. कब वो कॉल हो पाएगा? एक तो बोले कि interrupt. The process has to be come here and the interrupt will be joined. Once the interrupt will be joined, it has to do it. Anybody else?
Sir, when the process gets over and or when the IO is taken.
During the exit function call? During exit function call?
Sir, an IO.
Yes, very nice. Then also during any IO operation. Yes, means inside the exit function, you may find a scheduler may be called if it is a exit function. Similarly, when any IO operation will be there, since I am coming out because of a required IO operation, I have to call immediately scheduler. Then I have to come out. So in this three scenario, the scheduler is called. And this kind of this, which scheduler? The short-term scheduler, which is called as the CPU scheduler, that will be executed very frequently. What is the reason why it is executed very frequently? If it is not executed very frequently, what's the problem occurs? Anybody?
Not able to maintain the ready state.
No, it is maintaining a ready state. What's ready state is there, but I am saying from here to here.
Send to the running state. We don't know then.
One thing you can point out that if your this short-term scheduler will be run after a long period of time, then the response time will be quite high. Yes or no? Because after a long time, one process will get a chance to be executed by the CPU. That may be also there. Means you can find a delay, because you can find that one process is currently running then another process after some time it is entering into this. But if it is do very frequently, like last first 2-3 classes I told, if a barber is doing very fast, मतलब एक आदमी का थोड़ा सा काट रहा है, एक आदमी का थोड़ा सा बहुत फास्ट घूम रहा है, one from one person to another person. In that scenario, a customer cannot feel that the barber is actually moving from one to another. But if we really the barber is going very slowly, moving from one to another or cutting a particular person's hair little more, then he is going to the next, then another person will feel that I am really sitting ideal and not doing anything. So that's the reason this particular thing has to be done little faster or frequently. But most important kind of scheduling, one more, is called as the long-term scheduler. And this long-term scheduler is called as the job scheduler. Long-term scheduler, little theory today, this is job scheduler. So why it is called as a job scheduler? What is the reason behind this? He is saying it supports to increase throughput in multi-programming system. Multi-programming system. Now the question comes, before going into this, because I'll just draw a little bit. This is my new state. This is my ready state. And this is the running state. This is the termination state. This is the blocked state. There is another state. There is another state. So you can, what is this state name? Ready, suspended. Ready, suspended. This is block, suspended. And here it is swap out. This is swap in. This is swap out. Sorry, this is swap out. This is swap in. This is entering. This is also entering. This is here. This is here. This is here. And we told here the short-term scheduler work. Yes. So what about this long-term scheduler and where this long-term scheduler work here? So basically the long-term scheduler will take a decision that which processes will be entered into the ready queue. Basically what is saying, the long-term scheduler takes a decision about which processes will enter into the ready state or ready queue. Yes. What is the why it is related with the job scheduler? Why the name is called as job? The short-term is called as a CPU because it is giving the task to the CPU. But in this case, where the long-term scheduler then works? The long-term scheduler basically works here and here mostly. Because he will take a decision who will enter into this ready queue. He will also take a decision which will enter into this ready queue. And here somebody will say, but since our swap in and swap out will be mostly done by a medium-term scheduler, we take a decision. So these two are purely a long-term scheduler's work. Means from the new, one process enter into the ready, and from this block, one process enter into this ready state. That decision has to be taken by a long-term scheduler. Then why it is called as a job scheduler, and what is this meaning of supporting increasing throughput of the multi-programming system? So there are two kinds of job we studied. One is called as the IO bounded job, and another one is called as the CPU bounded job. Yes, we know that in case of IO bounded job, more work has to be done by IO bounded. IO operations. In case of CPU bounded job, more work has to be done in a CPU related things. Now, if your long-term scheduler only sends the CPU bounded job, can you guess that what is going to happen now? Suppose this long-term scheduler will send most of the CPU bounded jobs to the ready queue. Then what will happen? Anybody?
Sir, after having the IO input, then also it will be still waiting.
So you can say that your if more number of processes are coming into the ready queue, then the CPU will be busy, but your IO operation will be completely blank. Means no IO is working here. Means more jobs are frequently entering into the CPU and coming here. So the total waiting time will be increases a lot. In another scenario, we can go for this. Suppose I am going for only IO bounded. If you are sending only IO bounded jobs, then process comes immediately running for a few seconds, come to this IO because he needs more IO. Then what will happen here? The IO queue becomes filled up, whereas the ready queue becomes gradually empty. Because many processes comes to the ready queue and immediately they come here to the IO queue. And since my IO queue needs a lot of time, that's why your ready queue becomes empty. So that's the reason what is saying the long-term scheduler take a decision in such a manner that your ready queue is basically a combination of both IO bounded and CPU bounded jobs. If both kind of jobs will be sent it to this ready queue, then your CPU running state as well as the block state can be properly balanced and maintained in this way. So that is saying it is a job scheduler because it is provided the job to the whole system in such a manner that neither the CPU becomes idle nor the IO becomes keep quiet. So both CPU is also running and IO operations is also simultaneously going on because our long-term scheduler could able to send a mixture of IO bounded and CPU bounded jobs to the ready queue. And at last, there is a medium-term scheduler. The medium-term scheduler main responsibility is to make a swap out and swap in. In many operating system nowadays also, we remove this medium-term scheduler, but the working principle is still there that whenever the memory is not available, it has to be bring it to the swap area. Okay, so this too plays very important role, but you may not say, you may say that there will be no medium-term scheduler required. Is there any scheduler required here? In this transition? Quick, is there any scheduler required in this transition?
Sir, there is buffer.
There is no transition, no scheduler required because a process has to be come out. What scheduler you require? He is saying kick him out or chale jaiye, then he has to come here. So there is no requirement of scheduler. Is there any scheduler here also? There is no requirement. It is also kick him out. Here he himself is saying that I am going out today. So there is no scheduler, no scheduler, no scheduler. In other parts, you can find a scheduler. Because here you are finding short-term scheduler, here you are finding long-term, here you are finding long-term, here in both swap out, swap in, swap out, swap in, some long-term scheduler will be, medium-term scheduler will be. So this is basically the CPU state transition diagram. And in your book, you may not find these two things. Rather, you can find only new state, ready state, block state, running state, termination state. And they will give you one more interesting diagram they are saying. Here they will make you a medium-term scheduler. They are saying the processes when a memory is not available, they will go to some swap area by swap out and swap in. But since you have maintained these things, no need to draw this diagram once again. Okay, just you maintain the way you have discussed. So that is basically called as the state transition diagram. Is it clear? No need to remember these things. I hope you have remember the whole diagram in your mind. New se aayega, ready se running, running to block, block to again ready. From the running, it has to be go to the termination state, and from the block and the ready, there is a suspended state. Okay, and from the block and ready, when it is come to the suspended state, that scenario already you have discussed, when the memory is not completely available. Okay, this is one kind of things people will ask. The next interesting thing, what is a context switch? Last class I told what is a context switching when it is required. Anybody? Participation only one person. Why? Yes.
The moving from one process to another process.
Who is moving?
So the CPU.
So he's saying this is a mechanism. कुछ तो चाहिए ना? This is a mechanism to change the control of the CPU. From one process to another process. One process to another process. Like then if your quantum time is 1 unit, Qt becomes 1 unit. And if during this 1 unit only one line will be executed, after execution of this line by the CPU will be switched to this one. Once it is over, then come to here. Once this is over, again come to here. So like this, the CPU will be changed from one process to another process based on this Qt or quantum time. So when he is moving his control from here to here, that is basically called as the context switching. Means switching the context. What is the context here? The context is basically your CPU state. Sorry, CPU state. Yes, what is the CPU state? Anybody? What is the CPU state? Others, not the same. What is the state?
Registers.
Yes, very nice. The registers associated with the process. Associated with the process. Why I am saying I have discussed already, but sometimes theoretically they will ask, you have to say that as aapko pata hai. So what works during this time? So if you can consider it is a P1 and it is a P2, I told that some registers are associated with this. Let's take it is currently running. Yes, running. Once it is running, suppose now the CPU wants to change from P1 to P2. So what it does, it saves its context. Save the context. Yes. After it is saved the context, then which process will be started? Anybody? Which process will be started? The P2, the next P2. So from here to here, the P2 is becoming idle. Yes, he is not doing anything. Then what he has to do is to start this process. First, it will be load the CPU, load its context. Load the context. Yes, once it will load the context, then the execution gets starts. So it is running now. The moment this running gets over, means quantum time gets over, again he has to become and he has to do save the context. Save the context. After he will save the context, then again he has to idle for this moment. This is idle. After this become idle, now he will do the load the context. Yes, exactly it is happening. And from here to here, it is gets running. And from here to here, it is again become idle. Yes, so it is loading, unloading, loading, unloading. So he is saving it and his context will be loaded. And once it is over, then it is saved and another context will be loaded. Like this, the CPU is changing from one to another, and this is basically called as a context switch. Yes, so with this, we studied that how a process created, how to execute, what are the state it has to be moved, and this. Can anybody guess that how a scheduler program will be written? Suppose one running state to ready state, a process has to be go. Can you think of anything how a scheduler program will be written? How it is changed? Okay, very interesting. One small scheduler program, you can think of this. Always, every operating system maintains a process table. Okay, process table. This process table is nothing but an array of processes. This is an array of processes. And you can say there is a P9, P2, P5, P7, like this, he has kept it. What are those? These are nothing but a PCB. Means if you can say that this is my array, this array keeps the PCB of each individual process. Or you can say that the pointer to the PCB of each individual processes, that kept it inside a process table or an array. Then where a scheduler starts, inside the scheduler, basically this kind of program will be written. I'll show you sometime. You can start a for loop. There is a P, E is equal to start from the process table. Yes, he will make a link to this process table. Think this is the P, and gradually this P is going to be incremented. Yes, this P is going to be incremented. Then what should be written? If it is in the ready queue, then it will go for the running. If it is not in the ready queue, nothing is happening. So first checking P9. What is the state of this P9? So how can you know the state? He will be written. If P9s means this, means you can say that it is P0. P0 dot state is not equal to ready, then it is going to be running state. Continue. Yes, if not, means if it is not in the ready state, you search for a next process. You search for a next process. If it is really in the ready state, means it will come here. In the ready state, what you have to do? You have to basically now give this process to the CPU. How can you give it then? There is a CPU, and inside the CPU there is a proc. The CPU says that which process control block he is going to be run now. That is P of this I. You can say I. Okay, P of I. Then once it will make it, then you will make this P of I's dot state is equal to running. So kya? He was in the ready state. Since it is in the ready state, if it is not in the ready state, continue. Suppose it is in the ready state. If statement execute nahi hoga, yahan aayega, and that process from this table will be assigned to the proc. Yes, once it will be assigned to the proc, then you will set this processor state to be running. Once it will become running, then there will be a switch to this process. Yes, means now he will make a context switching here. So this is basically a context switch. Yes, this is usually written inside your scheduler. If you can look into any scheduler of x86 or any kind of operating system, there is a process table which is infinitely running. Why it is infinitely running? Because there is no such condition. He will be continuously check this, check this, check this, check this, check this, check this, again check this, like this it will be running unless until you forcibly switch up the machine. Yes or no? So that's why there is no such condition, rather it is continuing, and every process you will bring from this table, check that if it is ready or not. If it is not ready, then obviously continue, go for the next this. If it is becoming ready, then you will fetch this process, assign it to the CPU. Once it is CPU, then change the state, then make a context switching. So you will tell to the process that now you are ready for the context switching. So this is exactly happening. I'll show you so that you can get an interest. Otherwise, theory just like it.
Sir, but there must be a size of that arena.
Yes, there is a size of the array. Size of the array. You tell me what should be the maximum size of the array.
So that process ID maximum length.
No, the number of processes can be created at a time. Maximum number of processes can be created at a time. Can be considered as the size of this array or not?
Yes, sir.
Yes or no? So how many processes can be created at a time? हम लोग पढ़े कितना प्रोसेस एट ए टाइम क्रिएट कर पाएंगे? बोलिए उस टाइम तक मैं
2 to the power 16.
2 to the power 16. Very nice. Means you can say that many size I can create an array. Nothing wrong in that. 65,000 size is not a big array. Yes or no? As per the computer is concerned nowadays, 65,000 array size is not a big array. And each element of the array will be representing what? It is pointing to the each individual PCB. Have you remember what is the PCB structure name? Last class पढ़े थे? याद है या भूल गए? यस बोलिए, सुनना चाहता हूं आप लोग से, नहीं तो आप पढ़ने रहे हो, बस मैं यहां बता रहा हूं, आप जाके फिर खत्म हो गया फिर आपका काम। यस एनीबॉडी, कितना बोल पाओगे? What I ask? What is the process name? What is particular process PCB's name? यहां पर भी दिखाई दे रहा है स्क्रीन में, बोल पाओगे? PCB structures name, which one?
The PID.
Process control block structures name. What are present in the process control block structure? पढ़ाई नहीं हो रहा है, नहीं हो रहा है।
Struct proc.
हाँ, ये पूरा लिखा गया है, देखिए यहाँ पर है, इसलिए बोला स्ट्रक्ट प्रोक। क्या क्या होता है स्ट्रक्ट प्रोक में? What is present in the PCB?
Process state,
Process
PID.
ID.
Process state, process ID, parent process ID, CPU state, yes, scheduling algorithm information, all these things are file information, memory information, all these detail was present or not? So this is it. So if you can go to one scheduler, the simple scheduler, just look into it how it is doing. Yes, are you getting this? See, this is simply an infinite loop. Yes, what it does, he chooses a particular process from this for loop. Yes, he choosing from the process table. P table is the process table. He fetch it this. Once he fetch this particular P, then he checks whether my P is a runnable or not. If it is not in the runnable state, make it continue. If it is in a runnable, runnable means as per this XP6, runnable means it is a ready state. Okay. If it is not in ready state, continue for the next process. If it is in the ready state, then what he does, he assigns this P to this process, to this CPU. C stands for your CPU. Okay, which CPU? And this CPU, if you can go to the CPU, there is a parameter called as a proc. If you go here, that is this C. There is a parameter called as a proc. A CPU के अंदर जो CPU भी एक structure है, under this there is a proc. In this proc he has said that. Okay, he has set this here. Yes, then he is saying he changed the state and telling that you now make a context switch. So here actually the P state will be changed the context. As I have shown a small diagram now, it will save the context, load the new context. It is going to happen like this. Okay, now you can see here where the scheduler has to be called. This C dot scheduler is the current program which is running. That has to be context switching with whom? ये अगर समझ पाओगे, मैं समझ लिया कि आप 60% अभी तक समझ लिए, बोल पाओगे?
Sir, with
Switching
the current one.
है?
Sir, with the current process.
No, scheduler के साथ हम तो सीखे अभी P1 P2 के साथ हो रहा था, कि scheduler यहाँ पर कहां से आ गया? Are you getting my point? I told that the P1 is context switching with P2. Now here I am saying a scheduler is context switching with the P.
Sir, because after that process, then the scheduler runs, we have to context switch with that only.
Oh, very nice, very nice. Yes, suppose let's take now P1 was running in the running state. Yes, now next process should be P2. Can your P1 brings the P2 directly?
No, sir.
कौन इन्वॉल्व होगा फिर?
Scheduler.
Scheduler.
हाँ, तो क्या होगा फिर? P1 P1 and scheduler के बीच में पहले context switching होगा. Now who is currently running? Previously CPU यहाँ था. When the context switching occurred, then who is starting now? Here the CPU is running. The CPU is running which program? Scheduler program. Then इस scheduler से मैं P2 को जाऊंगा या P1 को जाऊंगा? P2 को जाऊंगा. Then the context switching has to be done between whom now? The scheduler and the P2 or not. That's the reason here it is saying that the context switching is done between the scheduler which is currently running and the new process which is currently selected. Are you getting my point? Otherwise you can say, sir, previous process के साथ एक context switching होना चाहिए था. This switching is basically the context switching. If you can look for this also, here it will be written that how he has saved the context, how he can load the context and unloading the context. All these things you can find out in this particular switch statement. Okay. So this is a very, very interesting and powerful statement where don't never think that it is doing from the one process to another process. Rather, yes, that is correct. But here the process is not my original process. Here the process itself is a scheduler because my original process has context switching with the scheduler. And now currently the scheduler is a process. If the scheduler becomes a process, by his process he is taking a decision that which new process is going to be executed. That's why he has made a context switching between the current process with this one. Okay, that is the idea of this. Okay. So in this way, yes.
Sir, here the P2 has given the charge to the scheduler. After that, after it has executed, then we have to context switch the P1 and the scheduler. Sir, so we have done that now, yes, swapping. So because P2 is given to the scheduler, so if we swap the scheduler with the P1, then it is working now. Why we are scheduling? Why we are context switching with scheduler and P2?
Oh, why you no? When P1 was running, the P1 has to be move out. During the move out, do you think that there is no context switching?
Oh,
होगा ना?
first P1 and scheduler, then after that we will do the new one and scheduler.
Yes, that's why I wrote here. No, first P1 run कर रहा था CPU में. जब वो बाहर आएगा, उसका जो information उसका start में save होगा कि नहीं? It has to be saved, no? And this scheduler's information has to be loaded. Means there is one context switching here also. After doing these things, now you are thinking about which process the scheduler will be select newly. That process is P2, and the scheduler itself has to be context switching with the P2. Okay?
Yes, sir.
Yes, fine. Thank you. So this is about this. Now we will go for another interesting part, that is called as, we know about a process, but another interesting feature of the operating system is called as a thread. Yes, this is the powerful feature. Every time we are using it in any kind of applications, or mostly in the gaming application and these things, you are using a thread. Now you can feel there is sometimes you are preparing a game. In the game, a ball is moving. Today also, if we can comfortable in any graphical user interface languages, you can follow. A ball is like this, moving like this, and one kind of a missiles is going. Yes. So when it touch it here, then it is going to be destroyed. Otherwise, some point will come. And if you can look into it, there are two things are working simultaneously. One is moving this missile and moving this ball. Both are not going one after another. Rather, both are doing it simultaneously. Since this is one thing has to be done at the same time, this is also going on, means both the things are done inside the same program at the same time. That can be done with the help of either by a process or by a thread. So either by a process means what? This is one process P1 and this is one process P2. Both the processes are running simultaneously. But the same thing can be also done by, this can be considered as a one T1 thread and this can be considered one T2 threads. Now the question comes, already you have studied, sir, through fork how to create this P1 and P2. And we know how to distinguish the parent and child. Inside the parent, I'll run this, and inside the child, I'll run this. Then both will be run simultaneously, because we have seen if there is some statement present in the first process, some statement present in the second process, both the processes will run simultaneously. We have seen it's A, it's B, it's C, it's D. In which sequence they are running, that also it is not in our control. Rather, it is executed by the CPU as per the operating system scheduling. Okay. So since it is happening by a P1 and a P2, then why you want to create the threads for doing the same work? And what is the purpose of here making this thread? So what is the thread means? The thread is called as a lightweight process. Yes. What does it mean? The lightweight process means that every thread uses the address space of its parent. That's the reason it is saying that it is a light. Means what? When P1 process was there, you create a P2 processes. We discussed that the whole address space is going to be copied to this P2. Means P1 and P2 are the two different address spaces. And there is no common feature in between these two. But what this thread is saying, if P1 is a one process, if you want to create another thread called as a T1, then this T1 is going to use the address space of the parent process. He has not its own address space. Rather, all the threads created under this P1 has to be used the address space of this. What does it mean then? Suppose assume there is a global variable present in the P1 called as A equal to 5. Since T1 and T2 are the two threads created by this P1, then both the threads can use this common A which is present inside the data segment. Means the T1 and T2 are also processes, but it is not a purely full process. Rather, it is a lightweight process. But both processes can use the same address space. Then what is the benefit? The benefit is that when you want to do a context switching between one process to another process, then a lot of things is going to happen during that context switching. We see you have to save the all registers context of the P1 and go to the P2, and P2's context has to be loaded. But in this case, since the T1 and the T2 belongs to this P1 process, the context switching time would be very, very less, because everything is available in the common area. What's the needing? What is the necessity of making a context switching, saving everything of P1 or saving everything of T1 and starting its T2? Because T1 and T2 is using the same area. So that's why the people are preferring this particular thread. One reason is that it is a lightweight because it is using the common address space. And another thing you can say, because of the common address space, the communication between the T1 and the T2 will be quite easy. There we studied a new things about a pipe. We have to establish a pipe between these two to communicate. But now we can quickly say, to communicate between the T1 and the T2, my global variable is sufficient. The reason? Because this is the same memory used by both T1 and the T2. Yes, even if this T1 and the T2 will be running simultaneously. Okay, that is a basic overview I have given. So let's check how you can create a thread and how it is different from a normal programming language. Suppose I have a main, and inside the main, please participate. That is a statement 1, statement 2, F1, and this is statement 3, and this is my F1. And inside the F1, that is a statement 4, statement 5, and statement 6. And we all know that the process execution starts like this. First, it will execute this, execute this, execute this, come here, execute this, execute all this. Then again, it has to be returned back. Then from here, it will be executed. Means, if there is a function called main, in between inside another function. When the function call is called, unless until that function gets over, the control cannot return back to the original function. Yes, this is the normal approach which you are following in case of a function call. But same thing how the thread is working. Yes, but what the thread is saying, if I have a main and inside the main same lines are present, first S1, second S2, and I create a thread here. Suppose I create thread. And please remember, every programming language, when they are creating a thread, they will pass one function. Yes, means they are saying, what is the working principle of this thread? The thread's work is to execute F. The F is already there. The F is a normal function. The way you have written here, that is S4, then S5, then S6. And here also there is a statement called as S3. Now the same thing exactly, I call F1, but here it is saying, no, you don't call F1. You create a thread whose work will become F1. Yes, and the same F1 can I also call here. Two things I see. The F1 is used as a thread and called, and F1 is normally called. Both I will show you by program. Okay. Now how the execution takes place in both the cases. We know here, if a normal call will be made, then unless until the F1 completed, the control cannot return back to this place. But what about this? He's saying, first execute this statement, then this statement, then this statement. The moment it comes here, now, there is another context starts here. Means, this is a one process, indirectly we are saying it is a thread, and this main process is come to this place. Means there are two processes simultaneously running in the CPU. Then which one will be executed? This thread T1, which is created here, he is reached here to execute this one. And the process who has created this thread, he is coming to this place. He is not waiting. He is just shouting, hey, thread T1, I have given you this F1, you please execute that. And after shouting, he himself come to this place to execute his place. And what happens here? The happening is, this P1 process is now executing S3 onwards, and a P2 T1 thread is executing from S4 onwards. Means now there is a two indirect processes are running. One is become P1, which is started with S3 now, and one is become T1, which is started with this S4 now. So both of them are running simultaneously, where you can feel that this is also a kind of process which will be executed. Now what is the problem? In this case, he's saying, in case of function call, it has to complete and return back, but here it is not. Here he just called and you yourself come here, he is here, he himself stands here. Then once this T1 completed its job, it will never return back to its original place. Because after this line, it looks like one independent process, which is executed by the CPU separately, and this is also executed by the CPU separately. Then you can feel that I have created two kinds of processes. One is T1, one is P1. Like we are creating by a fork, there is a P1, P2, here also you can. So if I create a one more thread equal to create thread F1, then what happens? This F1 comes here, now the control comes here. Again, there is a one more thread pointing to this called as a T2, and your P1 comes here. Now, how many processes? Three processes. P1 is my original process, T1 is my one thread, which starts from S4, and another T2 will be also start from S4. When both this T1 and T2 executed S4 onwards, and my P2, P1 is executed from S3 onwards. But when this P1 comes to this place, now you can feel the same P1 again executed S4, this T1 also executed S4, this T2 also executed S4. But what is the difference? Now you can say, so same thing we are doing in the process. But see, if there is a variable called as a int k equal to 5, then if this fellow has incremented k plus plus becomes 6, if you want to print it here, it will become 6. Why? Because there is only one memory area created for K, and all these processes, or sorry, main process along with all the threads are using this common area. That is one beauty of this particular thread. So
Sir,
let's program this. Okay, itna hi today.
sir, sir, but we cannot tell that thread 1 will show 6 only, because if the P2 has not reached that statement,
Yes,
then
very,
it
very
will
nice.
go to 5.
Manner, because since F1 is executed here, if he has first executed, obviously he may not display 6, no? He has to display 5. I told that if after this line, if it is executing, then it is going to that data or not. That I'm saying.
Mhm.
Okay. Fine.
Sir,
Huh.
sir, I have a doubt regarding that wait command, sir. How should we use that in that thing that you told to verify that if we are sending to the child and to its child and then receiving it back, sir, how to call that wait function? It is getting only the same thing, that pipe and thing.
No. So in this particular case, no. In
Yes,
this
sir.
particular case, one way will be, because if you, he has to wait for him, he has to wait for him, he has to wait for him. So at the end only you have to write a wait function. What is wrong in that?
Mm,
Because he is waiting for what? A input from the pipe. That will be read command must be there or not.
yes, sir.
The read command itself is waiting. No need for writing wait also.
Okay, sir.
The read command is itself is waiting, because unless until this fellow will be put something in this pipe, he could not able to read. So in this scenario, no wait may not be required. But in this scenario, you have to write. क्यों बोलिए तो क्यों देखिए देखिए this is depending upon him, this is depending upon him, this is depending upon him, means through this read he is depending upon him. इसका भी कुछ read होगा, he is depending upon him. इसका भी कुछ read होगा, he is depending upon him. So read itself making you wait. But in this case, all are independently connected with my parent. So here you have to write down explicitly wait with a while loop. Okay, otherwise it will not.
Sir, in the first diagram, sir, there we have to put that write data in the last after that for loop.
No, write data after the for loop. Not necessary. Why after the for loop I do it? Inside only. The moment I'll create this, now. Yes. When I'll come out, I'll do it. Yes, correct. In this case, I have to come out. After creation of this, I have to come out. Suppose I am writing a while loop. I'll write I equal to 0. I should be less than 4 or 3. Then I plus plus. Then I am making the t equal to fork. Then if t becomes positive, means if our t is greater than 0, then you have to make a break.
Yes.
Break means you come out here. Once you come out here, your first responsibility is you have to send it. So you have to send. How to send? You have to write some write command. And then you make a read command.
Okay, sir.
Yes, excluding which one? Last one.
Child.
And how to distinguish the last one? You know, by ith value. Because for him I is 0. Yes or no? For him I will be 1. For him I will be 2. For him I will be 3. So for I3 cases something. For other cases same thing. Okay?
Yes, sir.
Fine. But how to create these two pipes? Are you getting the idea?
Yes, sir.
Very nice. Thank you. Okay, I am ending now. हाँ? थोड़ा पढ़ाई नहीं हो रहा है, बोल रहा हूँ. हाँ, आप लोग, you are good students. How I am expecting that you are not remembering the things. Or from my side, if any mistake, you can tell me, please. अगर मेरे से
PCB है क्या वो प्रोसेस कंट्रोल
ब्लॉक
कंट्रोल ब्लॉक
क्या है सुन नहीं पाया. पीसीबी. हाँ, पीसीबी है
सर, वो प्रोसेस कंट्रोल ब्लॉक है ना.
हाँ, प्रोसेस कंट्रोल ब्लॉक है. करेक्ट.
ओके सर.
फाइन. ओके. पढ़ाई कीजिए, हाँ सब लोग जितना भी हो, 53 स्टूडेंट करेंटली प्रेजेंट, प्लीज रीड इट नाइसली। आंसर आप लोग को देना पड़ेगा, तब जाके मजा आएगा, नहीं तो मुझे लगेगा कुछ नहीं हो रहा है।
Yes, sir.
हाँ प्लीज। थैंक यू,
Yes, sir.
Thank you, sir.
थैंक यू
Yes, sir.
बाय।